Okay, guys. So this recording is from section 1.3. So section 1.3 is about complex numbers. Just complex numbers. So I just want to review that equation like this, x squared equal -1, has no solution in real number system. Because to solve this equation, we'll need to take the square root of both sides, and then we'll end up with x equal positive or negative square root of -1. And we all know that we cannot take the square root of negative numbers. So when we talk about real number system. So that's why this equation has no solution, because of that -1 under square root. However, we can solve this equation in complex number system. So we can solve this equation complex number system by introducing imaginary unit. So imaginary unit I such that I is equal square root of -1. So I is equal square root of -1. Okay, so we call that imaginary unit. So if I is equal square root of -1, so then I square will be just -1. So now when we know imaginary unit I, we can introduce complex numbers. So let me give you the definition of complex numbers. So complex numbers, that's the numbers which can be written in the form a plus bi, where a is a real part and b it's called imaginary part. Okay, so example, -5 minus 3i. This is a number in complex number system. A, in this case, which is a real part, will be -5. So that's the number without I. So this is the real part. And imaginary part, B, will be -3. So B is equal to -3. This is imaginary part. So imaginary part, it's the one without I, because I, -3, it's multiplied by I, and we know I, it's just imaginary unit. Okay. So what we can do with complex numbers, we can add complex numbers. So this is what we're going to do next, adding complex numbers. So to add complex numbers, a plus bi plus c plus di, so we have two different complex numbers. To add them, we just combine like terms. So we're going to add real parts together, which is a plus c. plus, and we're going to add imaginary parts together, b plus d. I. Okay. So just one example. We need to add 2 plus 3i plus 4 minus 5i. So since we have addition, we can remove those parentheses, 2 plus 3i plus 4 minus 5i. And when you add complex numbers, think about combining like terms. We're going to add real parts. So we have 2 plus 4, that will give us 6. And we're going to add imaginary parts. So imaginary parts are positive 3 and negative 5. So we have plus 3 minus 5. They both have I. Some factor that I outside. So we have 6 minus 2i. Since we can add complex numbers, so we also can find difference. So difference of complex numbers. So when you have complex number a plus bi, and you need to subtract the other complex number, c plus di, so we're going to subtract the real parts, which is a minus c, plus, and we're going to subtract the imaginary parts, which is b minus d. Okay, and I'm going to do an example. 2 plus 3i minus 4 minus 5i. So I'm follow the rule. I'm going to subtract the real parts. So I have 2 minus 4 plus, and I'm going to subtract the imaginary parts, which is 3 minus negative 5. So that will give us negative 2 plus 3 minus negative 5. This is just 3 plus 5. So here we're getting 8i. So we have negative 2 plus 8i. Okay. That's one way to do it. I just want to do one extra example. So this is example A. Example B. So we're going to subtract 6 plus 4i minus 3 plus 6i. So by follow the definition, I'm going to subtract the real parts. So we have 6 minus 3 plus, and I'm going to subtract the imaginary parts, which is 4 minus 6. And we're getting the solution, which is 3 minus 2i. Now, that's one way to do it. Also, what we could do, we could remove the parentheses, 6 plus 4i minus, since you have that minus, so technically that just tells you that you have negative 1. So you could distribute negative 1 to both, which means just change the sign to opposite. And now think about combining like terms. So then you have 6 minus 3, which is 3. And then we have 4i minus 6i, which will give us negative 2i. It's up to you how you want to approach. You can just follow the rule of difference of two complex numbers, or just remove the parentheses. Just remember that the minus in front of the parenthesis means change the sign to opposite and just combine like terms. So you always leave the solution real part plus imaginary part. So again, this is the same as 3 plus negative 2i. Okay. So we add complex numbers, we subtract, we also can multiply complex numbers. So multiplying complex numbers. So to multiply complex numbers, technically, just use FOIL to binomials. So we have two complex numbers, a plus bi times c plus di. So if you want to just follow the formula, so this is ac minus bd plus ad plus bci. And this solution straight comes from FOIL. I'm not a fan of memorizing that, so technically we're just going to FOIL. So you just need to FOIL. So we're going to practice, multiply. Okay, so we have a 3 minus 4i times 2 plus I. Okay, so multiply, again, I'm not fan of memorizing that formula, so what I'm just going to do, I'm going to FOIL. So F means multiply the first. So we have 3 times 2. O stands multiply outside, so that will be 2 times I, which is just 2I. I stands for multiply inside, so you have negative 4I times 2. L means multiply the last one, which is negative 4I multiplied by I. And now I'm going to simplify that, so we have 6 plus 2I minus 8I minus 4I squared. And now we just have to remember that I squared means negative 1, okay? So we have 6 plus 2I minus 8I minus 4 times negative 1. So let's simplify. I'm going to combine like terms here. So we have 6 minus 6I, negative 4 times negative 1 will give you positive 4. Combine like terms. So 6 plus 4 will give you 10 minus 6I. So this is the final solution. Always leave the answer in standard form, which is A plus BI. So 10, it's a real part. Negative 6, it's imaginary part. And maybe let's practice one more. Let's do one more. B. 5 plus 3I times 2 minus I. So we're going to FOIL. F stands for multiplying first. So we have 5 times 2, which will give us 10. O stands for multiply outside. So 5 times negative I will give you negative 5I. I stands for multiply inside. So we have 3I times 2I, which will give us 6I. And L stands for multiplying last. So we have 3I times negative I. And it's time to simplify. When I'm going to simplify, I also will combine like terms. So I have 10 plus I, minus 3I squared. And again, we have to remember that I squared represents negative 1. So that will give us 10 plus I minus 3 times negative 1. And we're getting 10 plus I plus 3. So combine real parts. 10 plus 3 will give us 13 plus I. So that will be the final solution. Again, what I did, I just follow. So this is how we multiply. Also, you can divide complex numbers, but before I introduce division, we need to introduce the definition of complex conjugate. So complex conjugate the definition is if z is a complex number in the standard form a plus bi, so this is a complex number, then its conjugate which we denote by z dash with the hat on top of it, is defined as, so the conjugate I call z dash equal a minus bi. So technically what we do, the sign of imaginary part change to opposite. Everything else stays the same. So I will just put here the sign of imaginary part change to opposite sign. Okay, so quick example. Find the conjugate of negative 2 minus 3i. So this is my imaginary number. So conjugate, which is z dash, will be equal negative 2, and the sign of imaginary part change to opposite, so plus 3i. That's it. That's the complex conjugate. Maybe let's do conjugate practice. Just one practice. Sometimes you may see problem like this, negative 2 minus 6i. So that means you have a complex number and you're going to see a dash on top of it. So technically that just tells you to find the conjugate of negative 2 minus 6i. So conjugate of negative 2 minus 6i will be negative 2 plus 6i. Okay, so the sign of imaginary parts change to opposite. So again, sometimes they may not saying find the conjugate, but when you see that dash on top of the complex number means conjugate. So now one formula which is very useful, multiplying complex number by its conjugate. So technically z times conjugate, the formula is a squared plus b squared. So you can use this formula when you have complex multiplied by its conjugate. And of course z, it's a complex number a plus bi, and z dash, that's a conjugate, which is a minus bi. So when you multiply complex by its conjugate, you take the sum of squares of the real part and imaginary part. So I'm not going to prove it, but technically the formula comes from FOIL. If I will ask you to multiply a plus bi times a minus bi and FOIL that, you will end up with that formula. I'm just going to give you one example how to use the formula. So find z times z dash, which is complex times conjugate, such that z equal to plus 3i. So we have a complex number. So I need to multiply complex by its conjugate. So conjugate will be 2 minus 3i. So we have z times conjugate. Z it's 2 plus 3i times conjugate, which is 2 minus 3i. Since you have complex times its conjugate, go ahead and use that formula, a squared plus b squared. So a, it's a real part, b, it's imaginary part. So I'm going to use the formula, a squared plus b squared. So we have 2 to the second power plus 3 to a second power. And that will give us 4 plus 9, which is 13. So again, this is what happened when you multiply complex by its conjugate. So now what we're going to do, since we know that complex times conjugate will give you always real number, complex number, okay, maybe that way, sorry. The product of a complex number multiply by its conjugate is always real number. Okay, like you see, we end up with 13. Okay, so there is no imaginary unit. Okay, so complex times its conjugate will always give you a real number. So knowing this, what we're going to do, we're going to learn how to write quotient of two complex numbers in standard form. So writing the quotient of two complex numbers in standard form. Okay, so this is important. Standard form just review that standard form of complex number is a plus b I, real part plus imaginary part times imaginary unit. So this is standard form. Okay, so we're going to learn how to leave the quotient in a standard form, and I'm going to explain that based on a couple examples. So we have 6 minus I divided by 1 plus I. So we have quotient of two complex numbers. We need to leave the solution not as a fraction. We need to leave the solution as a standard form. So how you guys always do those problems? The hint is multiply top and bottom of the quotient by the conjugate of the denominator. So hint, multiply top and bottom of the fraction, because technically quotient is the fraction, by the conjugate of the denominator. Always. So in our case, conjugate of 1 plus I is 1 minus I. So we're going to multiply top and bottom by 1 minus I. So we have 6 minus I divided by 1 plus I. I'm going to multiply top and bottom of my fraction by 1 minus I, which is the conjugate of denominator. Okay. So now you have binomial expression multiplied by binomial, which means fraction multiplied by fraction, multiplying numerators together. So we have 6 minus I times 1 minus I, and we're going to multiply denominators together. So 1 plus I times 1 minus I. Here what I'm going to do, I'm going to take care of multiplying denominators because we have complex times conjugate. So complex times its conjugate, it's a squared plus b squared. So in our case, a, it's 1, b, it's imaginary part. So our b will be the coefficient of I, which is 1. So we have a squared plus b squared. So we have 1 square plus 1 square. Not I. I, it's imaginary unit. B, it's the coefficients, imaginary part, which is, it's a coefficient of I. Okay. Here, when we multiply numerators together, what you need to do with numerators, you need to FOIL. Okay, so there's no shortcut here, you need to FOIL. So we have 6 times 1, which is 6. 6 times negative I, which is negative 6I. Then you have negative I times 1, so that's negative I, and negative I times negative I. And I'm going to start simplifying. So we have 6. Now I'm going to combine like terms. Negative 6I minus 1I will give us negative 7I. And here the product, you have negative I times negative I. So two negatives will give you positive. I times I, it's I squared. And from complex times its conjugate, we're getting 1 square plus 1 square, so that will give us 2. Of course, we still remember that I squared is just negative 1. So we have 6 minus 7I plus negative 1 divided by 2. Combine like terms. 6 minus 1 will give us 5. So we have 5 minus 7I divided by 2. Now going back to this problem, they want us to leave the answer in standard form, which is a plus bi, not a fraction. So now we're just going to split the fraction. So this is the same as 5 divided by 2 minus 7 divided by 2i. And this is standard form. Standard form. A, which is the real part, it's 5 out of 2. B, which is imaginary part, it's the coefficient of I, which is negative 7 over 2. So real part, imaginary part. Okay. Next, I guess I would like to do one more with the quotient. So let's do B. We have 2 minus 3i divided by 4 minus 3i. And again, we have to leave the solution in standard form. So what we need to do, we need to multiply top and bottom by conjugate of denominator. So conjugate of 4 minus 3i is 4 plus 3i. So we're going to multiply top and bottom by the conjugate of denominator, which is by 4 plus 3i. So we can leave the solution in standard form. So let's go back. We have 2 minus 3i over 4 minus 3i. We multiply top and bottom by the conjugate of denominator, which is 4 plus 3i. Okay. Okay. So let's take care of denominator first, because you have complex times its conjugate, which is a squared plus b squared. So in our case, a it's 4, so we have 4 squared plus b. b it's imaginary parts, which is negative 3. Okay. So technically, we're having 16 plus 9. Numerator, no shortcut. We need to FOIL. So we have 2 times 4, which is 8. 2 times 3i, which will give us 6i. Then negative 3i times 4, which is negative 12i. And then we have negative 3i times 3i, which will give us negative 9i squared. So let's simplify this. I'm going to combine those like terms here, and we're going to replace I squared with negative 1. So we have 8 minus 6i minus 9 times negative 1 equal. So we have 8 minus 6i plus 9 divided by 16 plus 9, which is 25. So 8 plus 9 will give us 17 minus 6i divided by 25. And we always have to leave the solution in standard form. So we're just going to split that 25 here. So this is the same as 17 over 25 minus 6 over 25i. Okay, and this is the final answer, standard form. The real part, it's 17 over 25. Imaginary part, it's negative 6 over 25. What else you can see in this section? Just a couple of theorems, I guess. I just want to quickly give you some theorems which you're allowed to use in section 1.3. So the conjugate of conjugate. So the conjugate of the conjugate is the complex number itself. So technically, this z, it's a complex number, a plus bi. And if I would ask you to take the conjugate of the conjugate, which is a plus bi, it's a conjugate of z, and then conjugate again, you will end up with a plus bi, which is original complex number. I'm skipping proving, okay? But just quick example, 2 plus 3i, and you need to find conjugate of the conjugate, so this is just original complex number, okay? You know what, let's just do the proof here. So conjugate of a plus bi will be a minus bi, and then if I ask you to find conjugate of the conjugate, which means a minus bi, and then find the conjugate of that, that will give you a plus bi, which is original complex number. So here it's a proof. Another theorem, the conjugate of the sum of two complex numbers equal the sum of their conjugates. So the conjugate of the sum of two complex numbers equals the sum of their conjugates. So here the theorem is you have a complex number z equal a plus bi, and you have w, another complex number c plus di. So if I will ask you to find sum z plus w and then take the conjugate of the sum, so what you can do, you can find the conjugate of z, you can find the conjugate of w and add the conjugates together. So this is the theorem. You're definitely allowed to use it. I just want to show one example how to apply. So we have to find, we have 2 plus 3i complex number plus another complex number, and they will ask you to find the conjugate. So instead of doing the operation, which is adding two complex numbers together and then take the conjugate, you definitely can use the formula. Z is the first complex number, which is 2 plus 3i. So you can break it down that way, 2 plus 3i, and find the conjugate of the first complex number, plus w is the second complex number, which is 4 plus 7i. And you can find the conjugate of the second complex number and then add the solutions together. So we're getting 2 minus 3i plus 4 minus 7i. And now I'm just going to find sum of those two conjugates. So we have 2 plus 4, which is 6. And then we have negative 3i minus 7i. That will give you negative 10i. So you can solve the problem that way. Also, you will end up with correct solution if you will decide to add complex number together and take the conjugate by the end. Okay. And another theorem, the conjugate of the product of two complex numbers equals the product of the conjugates. So this is another theorem. So technically what they tell you, when you have two complex numbers, z times w, and you have to find the conjugate of their product, what you can do, you can find the conjugate of z, then you can find the conjugate of w, and then multiply those conjugates together. Oops. So I want to show you the example of this theorem. So I have two complex numbers, 2 plus 3i times 4 plus 5i. So z it's 2 plus 3i, 4 plus 5i it's w, and then I have to find the conjugate of the product. So I'm going to use the formula. First I'm going to find the conjugate of 2 plus 3i. Then I'm going to find the conjugate of 4 plus 5i, and I will multiply those conjugates together. So conjugate of 2 plus 3i is just 2 minus 3i times conjugate of 4 plus 5i, it's 4 minus 5i. And now I will just follow. F multiply first one, so we're getting 8. O multiply outside, so 2 times negative 5, it's negative 10i. I stands for multiply inside, negative 3i times 4, which is negative 12i. L stands multiply last of each parenthesis. So you have negative 3i times negative 5i, which will give us 15i squared. So, of course, I squared is just negative 1. So we're getting 8. I'm going to combine like terms. So from here we're getting negative 22i plus 15 times negative 1. So we're getting 8 minus 22i minus 15. And that will give us negative 7 minus 22i. So always leave your final solution as a real part, a plus bi plus imaginary part. Last objective of section 1.3, it's about powers of I. I want to introduce that and show you the example because powers of I follow the pattern. So last part of this section is powers of I, which is imaginary unit. Follow a pattern. Okay, so this is important. And here the hint is the power of I repeat with every fourth power. Okay, and you're going to see that I, it's equal I. So technically this is I to the first power. I to a second power, it's equal negative 1. I to the third power, it's equal negative I, just quickly, because you can break it down that I to the third power, it's I squared times I, which is negative 1 times I, and that will give you negative I, okay? And I to the 4 power, it's equal 1, because I to the 4 power is the same as I squared times I squared, which is negative 1 times negative 1, and that will give you positive 1. Okay, and then everything will be repeating again. So I show you the explanation, so let me just erase that. And let's continue. So now I to the 5th will be the same as I to the first power, which is I to the 6th, it's negative 1. I to the 7, it's negative I to the 8, it's 1. And then you can keep going. I to the 9 will be I to the power of 10 will be negative 1. I to the power of 11 will be negative I, and I to the power of 12 will be 1, and so on and so on. So we're going to do a couple examples. Example, evaluate powers of I. So evaluating powers of I. So A, we have I to the power of 28. Of course, you can keep repeating that power and see how I to the power of 28 behave. But here what I'm going to do, I'm going to break that 28 as 4 times 7. So now using power of power property, so this is the same as I to the power of 4, and then everything to the power of 7. So this is power of power property. And I know that I to the power of 4 is just 1. So we're getting 1 to the power of 7, and this is 1. So I to the power of 28 is just 1. B, we have to find I to the power of 101. So here I'm going to also use rules of exponents. I can rewrite that as I to the power of 100. You know what? Going to do power of power again. So I'm going to rewrite that. Now let's do it that way. I to the power of 100 times I to the power of 1. So product of exponents with the same basis will it's equal to we adding exponents together. So now I to the power of 100, I'm going to rewrite as I to the power of 4, and then everything to the power of 25, because 4 times 25 will give me that 100, times I to the power of 1, which is just I. Now we know that I to the power of 4 is just 1. So again, we're getting 1 to the power of 25 times I. 1 to any power is always equal 1. So we have 1 I, and the solution will be I. So if you guys will have problems like that, use the rules of exponents. So the basic rules of exponents, a to the power of x times a to the power of y. This is the same as a to the power of x plus y. So that's what I did here. I rewrote 101 as 100 plus 1. Okay? So this is product property. So product of exponential expression with the same basis, it's equal sum of the exponent. Okay. Division property, the quotient property, a to the power of x divided by a to the power of y. This is the same as a to the power of x minus y. So this is quotient property. Of course, you can only use them when our exponential expressions have the same basis. And the last one, I only reviewing the most important one, a to the power of x, and then everything to the power of y. So this is power of power property, which tells you to multiply the exponents. And that's what I did with 28 right here. I rewrote 28 as 4 times 7. So I was able to use the power of power property. Okay, right here. Okay, and that's it from section 1.3. I hope that the notes helps. Thank you for watching.